Welcome everyone to the February 2nd, 2021 Open Planetary Lunch Talk. I'm Chase. I'm having coffee and not lunch. The idea to actually have lunch during this period has long since fallen by the wayside. It's a vestigial name. Our speaker today is Hari Nair from Johns Hopkins and APL, who will be giving a talk on imaging inside of Mercury's dark craters. Thank you for being here. When you're ready, just take over the screen share and start talking.
Okay, I'll do that right now. Okay, how's that? Good, okay. I'm Hari Nair. I'm at the Johns Hopkins Applied Physics Laboratory. And for the MESSENGER mission, which was the first satellite to orbit Mercury, I wrote the software to command the cameras. There was a narrow angle and wide angle camera used for a variety of things. And I'm going to go over one of the imaging campaigns that we had for the mission, which was to look inside Mercury's dark craters. Whoops. Okay. So Mercury's spin axis is almost perpendicular to its orbit plane. And so what that means is that the sun always sits right on the equator. And if you're at one of the poles, you would see the sun sitting on the horizon. So you can imagine if there is a crater at one of the poles, which there are, the walls of the crater might be high enough that the sun never gets above them. And so the floor of that crater will be permanently shadowed. And it can get extremely cold if the sun never shines. So from the ground, this was results from back in the 90s. Using radar images of Mercury, you can see these bright spots. I don't know if my mouse shows up, but there's a bright spot here on the North Pole. And it was thought at the time that this could be due to ice for exactly this reason, that you have these permanently shadowed craters at the poles that get very cold. You can trap ice in them, water or other volatiles, and they will be radar bright. And a little bit higher resolution Arecibo image. These bright yellow spots are the Arecibo radar returns superimposed on a map constructed from MDIS images, which is from Messenger. You can see these yellow bright spots line up very nicely with some of these craters. And thermal modeling of what the surface temperatures would be also shows that these craters would have very cold floors. So this shows the polar region down to, what is that, 75 degrees north latitude. And this shows the biannual maximum temperature. And it's biannual because Mercury is in a spin orbit resonance such that it takes exactly 2 Mercury years for one solar day to pass. So 2 years is 1 day on Mercury. So if you look at the maximum temperature at any spot on the surface over that Mercury solar day, you'll see that it's still very hot over most of this region. But some of these regions where the purple color is gets very cold, down to close to 50 Kelvin. And for comparison, Pluto's surface is something like 40 Kelvin. So some of the coldest spots in the solar system are here on Mercury. And so I'm going to focus on one particular crater, Prokofiev. All the craters on Mercury are named after artistic figures. And this particular one is Prokofiev, is one of the larger craters near the North Pole. And so here's just an image from MDIS, the narrow angle camera. If we superimpose the Arecibo returns, you see the region of it is radar bright. So what we did was we went through a bunch of images of Prokofiev taken at different times. And this would help us identify the regions that are always dark in all of these images. So this is a way to estimate what regions of this crater are always in shadow. And again, the radar bright returns line up very nicely with this permanently shadowed region. Another instrument on Messenger was let me before I get to that. And this is the thermal model superimposed on that. And again, this very, very cold region lines up very nicely with the radar bright region. So a lot of this evidence is pointing towards some volatiles, radar bright volatiles in this area. And these are returns from the Mercury laser altimeter MLA, which operated at about a micron wavelength. And so these dots here are the ground tracks over Prokofiev crater. And over this region, this radar bright region, you can see that the returns are considerably higher than outside. There's something like 0.3 on whatever the scale is in this reflected scale, whereas outside it's much lower than that. So, so we decided to try just taking a longer exposure image and stretching it, see, well, maybe we can see what's down there. Because if you were in this shattered region, you don't see the sun, it's true, but you would see scattered light from the rim of the crater around you. So they are dimly illuminated. So if you take an image of Prokofiev and you can see that a lot of it's saturated and stretch it, you still don't see a whole lot. And the problem here is something called frame transfer smear. And the way the CCD works is that you read out a line at a time. And if you have a saturated pixel on the CCD, that charge can overflow into the subsequent rows that you're reading out from the detector. And that can smear out and destroys the contrast, and you lose a lot of information that would otherwise be in the image. So the issue then is you can see these bright pixels near the top of the image that wash out anything below it. So what we did then was oh shoot, went over this without showing the slide. So this is talks about the frame transfer smear. And so here's a similar image of Prokofiev, except we targeted it a little bit more carefully so that the top of the image is inside this dark region. And this time when we stretch the contrast, we can see quite a bit of detail in this shattered region. So now showing those two side by side, you can see quite a difference in simply delaying an image being taken by a couple of seconds can give you a lot more information. And this requires to be accurate and precise when you target. So the way we scheduled Messenger was 3 weeks ahead of time. We'd have to use the best predicted ephemeris, and using that, we'd have to target our images. So the slide on, or the image on the left shows what we targeted, and the image on the right is what we actually got. So we wanted this edge, this blue edge of the frame is the CCD readout line, is the readout edge. So this is what gets read out first. And you want this to be in the dark region so that you don't have any bright pixels smearing out as you read out the image. So it was Prokofiev, which was this crater up here. And looking at another crater, Ensor, similarly, we looked at a bunch of regions, images of this particular crater, and doing the same trick with the with having the edge of the reader edge, which I assume is the edge on the right-hand side, inside the crater. You can see that stretching it, there's now a very dark border here inside this permanently shattered region that lines up with the radar bright area. So some craters have light regions corresponding to the radar bright areas, and some have dark regions. And what this could be is impacts due to comets, which are snowballs with a bunch of organic stuff mixed into it. So you can imagine that as the more volatile stuff of the comet evaporates, you'll leave behind these lag deposits, which can insulate the ice below it. The radar can penetrate these surface regions thin layers of organic material and still get a bright return, but visually they'd be darker than the surrounding area. So investigating these bright polar craters was a major science question that was answered by Messenger. This imaging wasn't initially part of the plan, but we thought, well, let's give it a shot and see what happens. And this this frame transfer smear problem, which is something this was baked into the hardware, was addressed by a software solution, simply delaying taking the images by a few minutes, or I don't know how long it was, a few minutes, seconds. And that's the end. So any questions?